Welcome back, and the topic for today's video is going to be an application or two employing the ideal gas law or ideal gas equation. So we remember from class that the ideal gas equation says that pressure times volume is equal to the number of moles of the gas times the gas constant R times the temperature. Alright, so the kinds of questions that come up where we can use the ideal gas law to help us out are ones where, for example, we want to know the molar mass of the gas, where that's going to be in terms of grams of the gas per mole of the gas, or we want to either use or obtain the density of the gas, where we're talking about the grams of gas occupied by 1 liter of the gas. Alright? So it's really sort of a units conversion kind of problem, where we sort of have to look at what we've got and then see how we're going to rearrange equations to get us to the units that we want. So let's take a look at a simple example of this. This is example number 17 on your handout, and it states here that we have a 0.418 gram sample of gas. That sample of gas has a volume of 115 milliliters and a temperature of 66.3 degrees Celsius. This gas sample is also at a pressure of 743 millimeters of mercury. So the question then is, what is the molar mass of the gas? Alright, so let's think about this. When we're talking about molar mass, we're talking about molecular weight. So what we need here is the grams of the gas divided by the moles of the gas. Now, if you look at the problem, we've got the mass of the gas. So that goes into the numerator. What we need is the denominator. We need to know the number of moles of gas that correspond to that particular mass of gas. Alright? So this is a perfect application of the ideal gas law or equation. We know that PV equals nRT. I can solve this for moles, where N is equal to pressure times volume divided by the gas constant and T in the bottom. Alright? Now we also know that if we're going to use the ideal gas equation in this way, we have to make sure that all the units correspond to the units in R. Alright? So remember, R is in terms of liters, atmospheres, moles, and Kelvin. So I started that process over here, where essentially what we need to do is we need to convert our volume in milliliters to an equivalent volume in liters, which we know how to do. And we also need to convert our Celsius temperature to Kelvin. We do that by adding 273 to the Celsius temperature to get the Kelvin temperature. Then the last one that I need to do is, I believe I need to calculate the atmospheres. Okay, so how do I do that? So I've got a pressure here in 743 millimeters of mercury. And we need a conversion to get us from millimeters of mercury to atmospheres. Okay, we remember what that conversion is. We know that for every 1 atmosphere, I've got 760 millimeters of mercury. Remember that a millimeter of mercury is the same thing as a torr. Alright, so millimeters of mercury will cancel with millimeters of mercury, and I will end up with 0.97763 atmospheres. And it looks like that's going to be good to 3 significant figures. Alright, so now I've got everything I need to substitute into the ideal gas equation here, solved for N. So my pressure is going to be 0.97763. It's atmospheres times my volume, that's going to be in liters, 0.115 liters, divided by my R. Now R, remember, is 0.08206. That's liter atmospheres per moles kelvins. Alright? And then we multiply by the temperature down there in kelvins, that's 339.3. And make sure our units end up giving us moles back. So let's check. So atmospheres will cancel here and here. Liters will cancel here and here. Kelvins will cancel here and here. Notice that the moles are in the bottom of the bottom, which brings them to the top. So my N calculated turns out to be 0.0040379. and that's moles of my gas. All right, that's going to be good to 3 sig figs, so we'll underline that there. All right, so now that I got my moles, what I'm going to do is plug this back into my molecular weight equation. So I have the grams of the gas, I need the moles of the gas, I can get that ratio. So let's do that. My N is 0.418 grams. And that's divided by my number of moles here. 40379. And keep in mind, this is my grams of my gas over my moles of my gas. Grams per mole is molar mass. And let's see, to the correct number of sig figs, I'm going to get 104 grams of gas per mole of gas. All right, so that takes care of that problem. In just a moment, we'll take a look at another quick problem. All right, so let's look at another example problem here. This is number 20 out of your handout. And this particular one deals with calculation involving the density of a gas. So let's look quickly at it. It says a particular application calls for nitrogen gas with a density of 1.80 grams per liter of the gas, measured at 32 degrees Celsius. So the question then is, what is the pressure of the gas in this system in millimeters of mercury? All right, so again, if I sort of deconvolute this based on what the problem is telling me, I've got a gas. And I know that this gas, because of its density, has 1.80 grams of the gas housed in a volume of 1 liter exactly. Okay? Units of density. It's a mass divided by a volume. I know the mass, I know the volume. All right. I have a temperature. Since we know we're going to use the ideal gas equation, I know that I need to convert the temperature over to Kelvin, which I've done here, adding 273 to the 32 degrees Celsius. Now it seems to me that what we need here is pressure, so we can get at pressure by using the ideal gas equation. All right, so we know that the ideal gas equation says that pressure times volume is equal to N times R times T. In this case, since I want pressure, I'm going to solve for P. So P is going to equal to nRT divided by V. So now we have to make sure that everything we want to plug into the equation is in the correct units. So it looks like I've got the temperature. That looks good. I've got the volume. That's in liters. All right? But the other piece that I need here is the number of moles of the gas. All right? I've got the mass of the gas, and I know the identity of the gas. I know it's nitrogen gas. So I should be able to, from the formula of N2, be able to get to the number of moles of nitrogen gas because I know what the molar mass of nitrogen molecule is. All right, so I can go ahead and do that calculation, and I end up getting 0.064255, and that's moles of N2. And that's going to be good to, it looks like, 3 sig figs. All right, so let's see if we can go ahead and make all the substitutions that we need to make. All right, so plugging into our equation here, I need my N. My N is 0.064255, and that's moles of N2, times my gas constant, liter atmospheres per mole Kelvin, times my temperature, and I said my temperature was 305 Kelvin. And all of that's going to be divided by the volume, which we stated in the definition of the density to be 1 liter. All right, so now when I work this out, let's make sure the units are good. Moles will cancel with moles. Looks like kelvins will cancel with kelvins. Liters will cancel with liters. I'm left with atmospheres in the top. That's exactly what I should get. And when I work this out, my pressure turns out to be 1.61 atmospheres. Now, I think the question asked for millimeters of mercury, so let's do that last little conversion then. I know that in 1 atmosphere of my gas, I've got 760 millimeters of mercury. So remember, a millimeter of mercury is the same thing as torr. So atmospheres will cancel with atmospheres. And when I work this out, I get to number of sig figs, 1.22 times 10 to the third millimeters of mercury. So that's going to be the pressure of the gas that satisfies the conditions set forth in the problem. All right, so we'll practice more with this in class, and we'll see you later.